All right, welcome back. So today we'll be just continuing to look at chapter 13, induction. So quickly, last time we talked about um, Faraday's laws on induction. So if you have biomagnetic approaching a coil, it will produce electricity in the coil, or if you are taking it away from the coil, then it also produce electric field in the coil. So fundamentally, it's the magnetic flux changing through the coil. So magnetic flux is defined as the magnetic field going through a certain area. So you can integrate to get this. So it's magnetic field B vector dot product of the normal direction of the surface, and then integrate through each small patches of the surface of dA. Then you get magnetic flux through the whole surface. Or if your magnetic field is constant, then you do B dot M normal direction and the surface area to get that. Okay. Um, so according to Faraday's law, then induced EMF or the electricity in the potential that causes the electricity in the coil is equal to minus of derivative of the magnetic flux over dt, where the minus sign is due to the Lenz's law, which says the induced current will oppose to change that cause it. Okay. If you have n turns of coils, then the induced EMF will be multiplied by n, the number of turns of coil. Lenz's law says the induced current always flows in the direction that opposes the change that causes it. Okay, so in this case, if you have biomagnetic field approaching, then the induced current will produce a B magnetic field that is opposed to that guy. Okay, or if you have this bias going away, taking away from the loop, then the induced magnetic field will be then in the same direction of original B field. We also talked about motional EMF. So that is any EMF. So this should be EMF instead of EMP. So EMF induced by the motion of the rod in the circuit. So if you have circuit here, this gets moving, then you induce a EMF. That is like you have due to this motion of this bar, it's like a battery. Okay, so now you have a battery in this place that is responsible for the electricity in the circuit. So induced EMF is equal to B times V times L for one loop. B will be magnetic field, and V will be the velocity of the motion of the wires moving. L will be the length of the wire. So then this is equivalent to have a B electric field in the rod, which that gives you B times V, which is basically the potential epsilon divided by L. Okay, in that sense. The force you needed to move the rod at constant speed then it should be equal to the magnetic force of F equal to ILB, which turns out to be B square V times L square over R. And the power of that force is equal to B square V square L square over R, just equal to the electric power in the circuit. So B square V square L square over R. So then the mechanical power is converted into electrical power in the circuit. So let's take a look on one more example here before we head on to the next section. Okay, so let me switch my camera. So this one says you have a short rod here, this small one, a length of A, moves with its velocity V parallel to an infinity wire carrying a current I. Okay, so infinity wire carrying current I. If the end of the rod near the wire is distant B away, so then the further side is A plus B. Okay, what's the EMF induced in the rod? So in this case, let me resketch the problem. So there's a wire carries current I. And there's this small piece of rod, length of A, B, going with the speed of V. So V will be the speed of it. Okay. So in this case, the rod is moving in the magnetic field produced by this guy. We know that this guy will produce a magnetic field. According to right-hand rule, thumb is in the direction of the current, and your forefinger curls in the direction of B field. So B field will be pointing into the paper on this side, out of paper on the other side. Okay. So something like that. Not uniform. Okay. Not uniform field, because as distance goes away from the source, then the B field decreases. All right, so this guy is now moving in this. So we can imagine what happens here is, let's say, let's look at maybe a negative charge here, right? Because this is a metal bar, so it's a conductor. The charge carrier is the electron, the electrons. So then look at electrons moving in this direction, right? So your thumb goes in the direction of that guy, your forefinger goes in the direction of B field, so kind of that way. So your palm is facing then in the direction of the force, so in that direction. But this is a this is an electron, so then the magnetic force or electron will be in that direction. So you have electrons being moving towards this side. You have negative electrons accumulate on this side, positive charges on the other side of this guy. So then this thing will produce a kind of electric field, right? Pointing in this direction inside this small piece. So then there will be potential difference across the two ends. Okay. So this is something similar to, if you can imagine, you have a rail, two rails, and then maybe there's a libel somewhere, or a kind of resistance there, right? So then this is moved by a distance of V times delta L. So it moved by now somewhere here. So this is V times delta T. So that's the distance travel, right? So this is something like if you have a circuit like this guy's moving, right? So then you can calculate how much flux change through this one, and then equivalently you can calculate how much induced EMF will be then on the circuit, right? So we'll be calculating equivalent induced EMF, which is equal to let's just take a look on the absolute value. So then derivative of magnetic flux over dt, okay? Or you can say, or just look at the change of flux over change of time t. So either way. All right. So change of flux in this case, right? So will be now corresponding to, you have increase of the area this much. Now your B field is also changing, so it's not uniform. So we probably just take like a small slice of this guy here, right? If this is small enough, then you can do B times this area change and then integrate through, okay? So let's say we are a distance r away from that rod for this B field, okay? So then B field in this case is equal to mu naught I over 2 pi r, okay? So change of flux, you can calculate it. That should be equal to now B field, right? Times the B field here times V delta T, right? Times dr, the increment of that guy, right? And then integrate from R equal to B, right? This end, and then to A plus B to the other end. So this is your change of flux, okay? So these two are constant numbers. You can put them in front of the integration. B field is mu naught I over 2 pi r, and then dr from B to A plus B. 2 pi mu naught I, they are also constant numbers. So mu naught I over 2 pi will come out, V delta T, and the integration of R dr, or 1 over R dr. A plus B from B to A plus B. So here, integration will give you natural logarithm of R, which from B, A plus B, okay? And then mu naught I V delta T over 2 pi. So that result will be ln of A plus B over B, okay? So mu naught I V delta T over 2 pi ln of A plus B over B to be your delta of phi. Now delta phi over delta T, that will give you your epsilon as an absolute value, delta phi over delta T. So everything divided by delta T. So mu naught I V 2 pi ln of A plus B over B then. This will be your induced EMF, okay? All right, so let's go back to the slide. So for induced EMF in the conductor is equivalent to you have induced EMF electric field there, okay? So in the electrostatics, so electric field is produced by charges in that sense. When you integrate through the whole enclosed path, like what we did for the Kirchhoff's rules, the loop rule, right? We get actually 0 epsilon. So epsilon is equal to 0 when you have electrostatic. But in this case, for the loops induced current or electricity, is actually it doesn't go to 0. So it's a certain number. Okay, so it's equivalent like it acts like just a battery. Okay, so for the if you have a rod, then you have two ends of rod, and there's electric field there. But when you integrate through the whole loop, it doesn't go to 0. Okay, so that's induced electric field. Closed loop doesn't give you voltage equal to 0. Okay. That's because the you do that, right? So this guy is not equal to 0. Okay. All right. So that's the difference of induced electric field and then the electric field by electrostatics. All right. Let's move on to the next section on eddy current. So one result of Lenz's law is producing eddy current in the metal or in the conductor. So if you have a conductor, if you try to pull it out of magnetic field, then there will be current induced in the conductor called the eddy current. So it's in the form of loop, and that's opposed to the motion. So then it's kind of you will experience resistive force. So there were several applications of that. One is for the electric brakes. So when the cars moving very fast, so then this is drum is rotating very fast. If you want to decelerate, you send in then the electric signal that produce this magnetic field. Okay, so then there will be eddy current generated that is that are slowing this drum very quickly. Okay. Also, you can use the magnetic field to damp oscillating metal plate in that case. However, if you cut into small pieces of the plate, then the damping effect will be very minimal because the eddy current then generate here in the will be in the smaller loops. Then the neighboring ones will cancel out the magnetic field produced by each other. Okay. But for like intact one, it will have a larger eddy current inside the plate, so then the magnetic field will be stronger, so that will damp out the oscillation faster. Also, in the recycling industry, the magnetic field can be used to sort the metals from other non-metal particles. Damping effect of the tri-balance, tri-beam balance. You can use that. There's a metal magnetic piece so that damps that out faster. Otherwise, it will just keep like oscillating. Application of eddy current will be in the metal detectors as well. So basically, there's a magnetic field here produced by current, and then if you swap it around, if there's metal underneath the ground, then will cause eddy current, and then will be interaction with the magnetic field. Okay. All right. So I think we have looked at the change of B field, change of area. Now let's take a look the electric generator, which actually is having changing of the angle the B field makes with the normal direction of the loop. Okay, so this is a schematic drawing of a electric generator where you should have a permanent magnetic field, and then you have fixed shapes of the coils. That means area is fixed. B field is fixed, but then this guy is rotating, so it generates electricity. So in that case, the angle theta is changing. So then the flux is changing. Okay. So the flux you can write out is MBA cosine theta. So a number of turns, the magnetic field strength, the area of the loops, and then cosine of the theta. So cosine of theta is changing as a function of time t. Okay, or if you do derivative of this guy, then it results in the sine theta will be equal to then omega times t, the angular frequency times the time t. So then the induced EMF in the coil will be N times, N will be the turns of coil, B is magnetic field, A will be the area, omega will be the angular frequency, and sine of omega t. So the electricity or electric signal generated then will be just a sine function. Okay, according to Faraday's law, you do derivative of the flux over dt. So let's take a look on one example here. It says you have a rectangular coil 25 centimeter by 45 centimeter, has 150 turns. This coil produces a maximum EMF of 75 volts when it rotates with an angular speed of 190 radians per second in a magnetic field of strength B. Find the B value. All right. So this is exactly what we have seen in the previous slide, where the induced EMF is equal to MBA omega sine of omega t. Okay, and it tells you the maximum. The maximum will be just equal to this guy when sine is equal to maximum, right? So it's MBA omega 75 volts equals to the turn is 150 turns. B field is what you're looking, and then A you can calculate 25, right, times 45. And so that gives you area, and then the frequency, it tells you angular frequency, so that will be the angular speed, 190 radians per second. Okay, you calculate for B field. So from this, B field is equal to 0.023 Tesla. Okay. All right. Going back to the slide. So electric generator, right? So it's basically you have the coils turn and then that generate electricity. Now electric motor is the other way around. You send in electric signal, then have current in the coil. So then the current in the coil result in the magnetic force on the coil. So then the coil will be turning. Okay, so the force will produce torque, then drives that. So the output is your mechanical output, the rotation. Okay, so input will be electrical input. So the electric motor is the reverse of electric generator. When you have electric motor working, so then because now this thing is moving, so then as a result, you'll produce EMF Okay, and then EMF in this case will be called back EMF because it will be in the direction that is opposed to the original EMF or original the driving EMF. Okay, so in that sense, so that could be small, or usually smaller than this guy, but if it's overspun, then might be greater than this guy. Okay, so as a result, actually, the back EMF reduced the effective voltage in the circuit. In that case, the producing lower power consumption of the circuit. Okay, so that's one of the advantage of the back EMF there. All right. Further application, so guitar pickup or microphones. Okay, so those two. There's a video here. You can click on that one and then watch on your own, but it explains how the pickup works. So basically, you have a magnetic field here on the string that is induced magnetic field by this external permanent magnet. Okay, so then as the spring is vibrating back and forth, then it's reacting with this guy. So then this guy will be moving back and forth, and because this is motion moving back and forth in the coil here, you'll produce electric signals. Okay, which the frequency of signal matches up with the frequency of vibration of the spring. Then the music produced by the spring will be then becoming the electric signal here, and that's connected to the amplifier. Okay, the same thing for or similar mechanism for microphone, because this when you sing the sound, your sound waves interact with the diaphragm here, makes this guy back and forth. The coils are situated with the diaphragm, so also move back and forth. So in this case, you move the coil back and forth with respect to the magnet. Unlike this case, the magnet is moving back and forth. Okay, but the same thing here. Electric signal will be produced here and then goes to the amplifier. Okay. The magnetic strips on your credit card works the same way. Okay, so there's a different patterns of the arrangement of the magnets in the strip. So then as you swipe it, the information will be read by the reader. Okay, the card reader. All right, so lastly, let's take a look on one example here. So this one says the long current wire, straight wire, and showing this figure, so current here, it's actually a sine function. Okay, so I naught is equal to 15, omega is 120 pi. What's the current induced in this rectangular loop at t equal to 0 and t equal to 2.1 times 10 to the minus 3 seconds? The resistance of loop is 20 or 2 ohms. Okay. All right, so then we need to know what would be the induced epsilon, right? At those two times to calculate the current, because current is equal to current will be equal to epsilon over R. Epsilon will be the induced in that. Okay, so to calculate epsilon, we'll be doing derivative of phi over dt, right? And then minus psi. All right, so that's this current I in the wire, and there's this loop. So similar to the first example earlier, okay, we'll actually say at this location R away from the wire, okay, so we can take that as a derivative of R small incremental R, so B field in this stripe is kind of homogeneous, so B equal to mu naught I over 2 pi R. So then the flux, because we need to use the flux, derivative of flux over dt to calculate that guy. So let's take a look on the flux first. Flux will be then equal to B field times dr, right? And then you integrate through from on this side to the other side. So let's call this A, and this Okay, so that's this is A because this is 5, and then this is also 5. So then this would be 2A. Sorry, my figure is not to scale, but 2A. Okay, so from A to 2A. A is equal to 5 centimeter. Okay. Or B times A rather, derivative of A. So this will be let's call it B. So small b. So the area will be dr times b, right? Times b. Okay. All right. So mu naught I over 2 pi r times b will be 8 centimeter. Okay. In dr. And then integrating from 5 centimeter to 10 centimeter. Okay. So this will be, the integration will be very similar to that guy because it's 1 over r. Okay. The rest are the um, constant numbers. Okay. So then the result will be whatever the constant numbers, mu naught I times 8, right? Centimeter over 2 pi. And ln of the upper divided by lower. So 10 over 5, that would be 2. Okay. Okay. But I is a sine function. So mu naught times I will be I naught sine of omega t over 2 pi and then 8 centimeter ln of 2. So then epsilon will be equal to derivative of net over dt. Let's just talk about the absolute values, okay? Because for the current, I think it doesn't ask for direction, so we can just use the absolute value and then divide the epsilon that divided by r will be equal to the I. Okay, so derivative of that guy. So that's now look at the numbers carefully. Mu naught is 4 pi times 10 to the minus 7 t m over a. I naught is 15 amps over 2 pi. And you do derivative to sine, it becomes cosine, and then omega cosine. So omega cosine of omega t times a times 10 to the minus 2 meters and ln of 2. Okay, so all this and this guy omega is 12 120 pi. Okay, all this other than the cosine, other than of the cosine, all other numbers multiplication and then divide by 2 pi, that gives you 2 times 10 to the minus 3 volts. So cosine of omega t. Okay. So then I naught for part A, I of t equal to 0, now I naught equals to so yeah, we are looking for the current. So epsilon over r equals to this when t equal to 0. So when t equal to 0, cosine is become 1. So then it will be just 2.00 times 10 to the minus 3 over r of 2 ohms. So 1.00 times 10 to the minus 3 amps. Okay. And b, when t equal to 2.1 times 10 to the minus 3. So we plug in t equal to 2.1 over there. Okay. And then divided by r. All right. So it's everything I of t equal to 2.1 times 10 to the minus 3 seconds equals to 2.00 10 to the minus 3 volts cosine of 120 pi times 10 to the minus 3 2.1 times 10 to the minus 3 seconds. Okay, and then over the 2 ohms. So everything will result in 0.703 times 10 to the minus 3 amps or 0.703 milliamps. Okay, that will be what you have on that guy. All right. So I think we'll just stop here today, and then we'll come back another time. Okay. So see you guys next time. Bye.